selection algorithms. All right, and we'll talk about 3 ways to do it. So selection is, normally we talk about sorting a list. That would seem to be the first step if you have a list and you want to do much of anything with it, is to sort it. But you might want to, you can find certain things without sorting. You could find the average. You just have to add up all the numbers and divide by the total number, and you can do that without sorting it. You could find the mode, the most common element, by just counting how many times each element occurs. But if you want to find the median, the middle size element, or the kth smallest element, it appears you'd have to sort the list to some extent, but it turns out you don't really have to sort the entire list to answer some of these questions, and therefore, if that's what you want, say the largest or the smallest or the second or third largest, there are ways to find that are faster than sorting the list, and of course, for small lists it doesn't matter, but for big lists this might really mean saving a lot of time. So the simplest way, of course, to understand is to just sort the list first. If you sort the list, obviously it's then easy to answer all those questions, but you have wasted more computer time than you needed to because you had to sort the whole list, and we talked last time about sorting algorithms, and they're all pretty costly. So if you have one way to do it is with a randomized selection based on quick sort. And we talked about quick sort before, but let's start with quick sort. So quick sort is divide and conquer. That's why it's fast. Whenever you're dividing and conquering under normal conditions, you'll end up with a term that's log n instead of n, because you keep dividing the list in half, and then half of it you don't need to worry about anymore. So you choose a pivot element, which you hope will be in the middle. Then you partition the list around the pivot, put the smaller ones on the left and the larger ones on the right. So this will take n comparisons. You'll have to compare each item to the pivot just once, but then you know which half it's on, and now you can ignore one half. Whatever you're trying to find, you know which half to look in, so the list keeps getting smaller, and that gives you a term of log n in complexity. So you choose typically the first element, is the simplest thing to do for quick sort. So now you just sort it into ones less than 45 and greater than 45, and now you only need to sort this smaller list or look in this smaller list for whatever you're trying to do. That's quick sort. All right. Then so in randomized selection, you take an unordered list and you just choose a pivot like this and partition it in 2 sublists. Then compare now the pivot, by the way, one thing to notice is the pivot is now in its correct position. If this is the 5th location, there are however many elements there are on the left, all these will only move within this sublist, and these will only move within this sublist. So you now know which one is at this location, which is location 0, 1, 2, 3, 4 in this list. I've now found the 4th smallest element in this list, I guess the 5th smallest and the 5th largest in this case, but the point is I now have found at least one of the elements, and I know where it is and it's not going to move. So if I was looking for the 5th smallest element, I'm already done. I don't need to sort the sublists. So that's a consideration. Choose a pivot, partition the list. Now see if that was the element you wanted. If it is, you're done. If it's not, you've still made progress. You now only need to look in one of the sublists, not in the whole list. So if we're looking for the 3rd smallest element, and we start with 45, well, it's not the 3rd, but now we only need to look in this short list to find it, and so it'll take many less comparisons to find it, and we will eventually find it by just looking in the next element. Again, taking the first element and just pivoting about it recursively will get us there. So it's pretty simple. Here's the code that does it, which is, this is recursive code, because remember you split the list and then you just continue using the same algorithm on the smaller list. So here we are taking the array list, we're starting and ending, and we're looking for the kth element, and after we do a split, we're only doing split plus 1 to end, or start to split minus 1, so that's how you look in a list that is hopefully smaller and hopefully half a size if your pivot happened to be in the middle. So the worst case complexity is order of n squared when all your pivots are on the end, so they don't actually shrink the list very much. That's the worst case.
And the best case?
The best case would be obviously when your first pivot is at location k. And so anyway, that's the game. So or n squared is the worst case, but I think your average case will probably be n log n, because you keep splitting the list in half. So deterministic selection, like randomized selection, is the same principle, but the idea is you're going to make a more serious attempt to find a pivot in the middle. Instead of just taking the first element, which will be in a random location, we're going to try to choose a pivot that's more likely to be in the middle. And the way you do it, the median would be the one that perfectly splits it in half. That's the one in the middle, but of course that would be expensive to find the median. So what we do is we split the list into groups of 5 or 8 elements, real short lists. Then we sort those short lists and find the medians of each group, and then take the median of the medians. So this is a relatively cheap calculation that will find something more likely to be in the middle. Not exactly the middle, but something that is likely to be in the middle. So you split it into groups of just 5. You sort these sublists of 5. You find the median of each one. Now you have 23, 52, and 34. So you choose the middle of them, which is 34. And therefore, you can see 34 is, you're now guaranteed, if you choose this, that a bunch of things are on the left and a bunch of things are on the right. So that's the idea. It's not perfectly the middle, but it's pretty close to the middle, and you had to go through a relatively small number of comparisons to get it. So that's the game. Your 34 is here. Now you sort the list into things less than 34 and things over than 34. And as you can see, it's pretty neatly split the list in half, so you're going to get that log n improvement. And so the worst case complexity is order of n. When all pivots are at the wrong end, I think that should be n squared. I think it's got to be more than, you had to do n calculations just to split the list one. I'm pretty sure that should say n squared. Let me just check in your textbook, because I'm thinking my slide has got to be wrong there, or else the book is wrong. You can't do this in n comparisons. It's got to be n log n or n squared are the only reasonable options. Let me go back to chapter 12. If you do n, that would be awesome, but I don't believe it. All right, so this is the implementation of deterministic selection. Okay, this is deterministic selection, and at the end they talk about how good it is. Okay, so yeah, deterministic selection improves quicksort. So in the worst case running, okay, when this estimated median is used as a pivot point, the worst case running improves from order n squared to the linear order of n. Wow. They really do claim that. Here we go. The median of medians algorithm can choose a pivot. This significantly improves the worst case performance from order n squared to order n log n. Now that I believe. It'll go from n squared down to n log n. Now what is this statement? The deterministic selective algorithm improves performance because the median of median finds the median in linear time, and when it's used as pivot point, the worst case running improves from n squared to linear order of n. I think this must be a mistake in the book. It looks to me like that sentence should be this sentence down here. I don't believe n. Do you understand this?
Not really. But
what's going out order? Yeah.
I do notice that they call them different things. The
yeah.
O n squared, they call that a running time, and the O n log n, they call the worst case performance.
Yeah, well, maybe there's a subtlety, but anyway, I think this should be worst case complexity is order of n log n. I think that is a far better description of, as far as I can understand, this makes sense. That's the idea. Of course, I think the worst case complexity would still be, I guess it can't be. You're never going to have your points at the end. I guess that's right. Even the worst case, you'll get n log n, because you really are splitting the list in approximately half every time. So anyway, this I believe. All right. And this cannot happen anymore. I'm going to get rid of this. You can't always have all your pivots at the wrong end anymore, because you chose the median of the median. That means there's got to be some on the right and some on the left. All right. Anyway, that I think is a better description of the situation. Okay, let's try a Kahoot. All right, which I got chapter 12 here. All right. to see if it's people having trouble. Sometimes they can't see the number or something. But I think I got the right position this time. That's it. All right, so which is the slowest operation? Sorting is obviously much slower. That's a lot more work. All the rest of these are intended to be faster, so you don't have to just sort the list. If you had to sort the list, there'd be nothing to talk about here. You'd just sort the list first and then find whatever you're looking for. All right, so which one partitions the list around a pivot? Yeah, both of them, of course. Randomized and deterministic selection both split it around pivots. The only difference is how you choose the pivot. All right, which one has complexity order of n? Uh-oh, I was afraid of this. Well, all right, we'll see. We'll see if I have the answer I thought was right or I made a mistake. Yeah, you know, yeah, you guys remembered. This is what I thought the answer was when I wrote these. The right answer, I think, is none of these. I think that's garbage. Well, you guys outsmarted me, which is good. I'm glad, because I can't change it at this point. That third one, I no longer believe. It said that in the book, but I don't believe it anymore. I think I was misunderstanding the book, or the book is wrong. I know in the next chapter the book's actually wrong at least one point. Anyway. That's the thing about textbooks. I often have to apologize for them. This is a pretty good book, but it does have mistakes. So